Hi everyone, Dr. Vaughn. By request, I'm going to make a short video about section 5.3, working with bases. So we're going to start with question 1, and we'll just do a similar question here. This time we're doing a base 8 system. We're going to look at 3, 7, base 8, and we want to go the number right before that. So we're just dealing with the ones digit, take 1 away from the 7, and you're right at 36. So, in all appearances right now, it works the same way. The only thing we really have to be careful of is when we're trading things in or borrowing from the next digit. So we'll see that in this next part, right? Because when we want to increment 3, 7, we want to add 1 to it, the next number, add 1. So we're going to have 3, 8. But of course, there's no 8 in base 8, only 0 through 7. So now I have to trade in that 8, make that a 0, and then this number of 8s is going to go from 3 up to 4. So we're carrying, in this case, up to 4 and then 0. The next question we're going to look at is number 2. The first thing is about the problem-solving method that should be used. This is the analogies principle. And then we're going to do a similar thing. This time we're working in hexadecimal, which is base 16. So right before 8F is going to be 8E. And now when we go after that F, which represents 15 in base 16, that's going to become a 16, and then we'll carry over to get the 9 again. Sometimes when you do this problem, you'll have the borrowing process, which is just trading in one of these for 16 of those. Some iterations of the question will actually ask you to do that. Next, we're going to look at question 5. And here we have this number 3,587, and we're trying to convert it into base 6. So we need to look at the powers of 6. So 6 to the 5th power is 7776. 6 to the 0 power is 1. So the number that's in this box here is just the power. And now I'm writing what 6 to that power is. So 6 in the second digit over, that's 6 squared, which is 36. In the third digit, we have 6 cubed, which is 216. And then in the fourth digit over, we have 6 to the 4th power, which is 1296. And then 6 to the 5th power, which is 7776. So it's important that I know these powers because this is the key to unraveling this problem. So I have this this number 3587, and I want to fill up the biggest powers first. So this 6 to the 5th power, this is too big. 7776 is bigger than the number that I have, 3587. So I can't put any 6 to the 5ths in there. But 1296 is smaller than 3587. So now I can divide 3587 divided by 1296. And you'll see that it's 2 point something, 2.75, I think. But there's 2 whole copies of 1296, or 2 whole copies of 6 to the 4th that I can put into this 3587. So I'm going to fill up this bin as big as I can, and then I'll figure out what the leftovers are. So 2 times 1296 is 2592, and I'm going to subtract that from the number that I started with. And that's going to give me 995. So now I'm going to do the same thing, and I'll follow the same process all the way down. So 995, how many 216s can I get out of that? 995 divided by 216 is 4 point something, 4.6. So I can get 4 copies of 2 to the 3rd out of the 995. And now I'll take 995 minus, I'll take 4 times 216 to see how much I've accounted for so far. 216 times 4 is 864. And if I take 995 minus 864, I get 131. All right, now we repeat this again. So I'm going to take 131. How many copies of 36 can I get in there? And again, you could just use a division. Divide by 36, you get 3.6. So I can get 3 copies of 36 out of 131. And then I'll subtract off the 3 copies of 36 that I've now accounted for from my running total. 131 minus 3 copies of 36, which is 108. So I have 23. And finally, how many 6s can I get out of 23? That's going to be 3, and that gives me 18 accounted for. So when I subtract 23 minus 18, I get 5, and that 5 is what's left over here. So now here's my digit, 24335 in base 6. 24335. All right, the next question that we're going to look at is number 8. And this is converting into base 16. So we're going to pretty much do the same thing. We're going to take the powers of 16 up until I get one that's bigger than 5401 and use subtraction to fill out these things from largest to smallest. So maybe I'll just copy this table over, put it down here under number 8, and we'll look at the powers of 16. We'll delete our little table here. We call this the base or chip abacus sometimes. So now we're going to start with the 0th position, and then the 1s is 16s, and now 16 squared. 256, and then 16 cubed, 4096, and that's probably as big as I need to go on this one because 5401 is pretty close to that number. If we multiply by 16, it's certainly going to be bigger than that. So I don't really even need these positions after that. So now out of 5,000, the number we're working with here in this case again is 5401. I can get one copy of 4096 out of that. So I'll subtract off that one copy of 4096. And that gives me 1305. So now divide that by 256. Gives me 5 point something. So I can get 5 copies of 256 out of that. I'll multiply 5 times 256. Get 1280 and subtract that from 1305. That gives me 25. And now out of 25, I can get one copy of 16. That gets me down to 9, and that 9 will go here in the last position. So I got 1519 in base 16. Didn't have to use any letters in this case. All right, and the last one that I'd like to look at here with you is probably the hardest one. I want to look at number 13. Now for this one, we're going to do a multiplication, 32 base 5 times 13 base 5. Now what a lot of people might do is change these into base 10 and then do the multiplication and then change it all the way back into base 5. But I want to show you a different way of thinking about it. And that is to just set up a multiplication table for your base 5 system. So here's 0 through 4, 0 through 4. 0 times 0 is 0, and that goes all the way across. 0 times anything is still 0 in a base 5 system. 1 times anything is still anything. 1, 2, 3, 4. And then 1, 2, 3, 4. Multiplication is symmetric. Now we're going to do 2 times 2, which is still 4. 2 times 3 is 6. 6 doesn't really exist in a base 5. So that's 1, 5, and 1, 1. So this is 11 in a base 5 system. And 2 times 4 is 8, which is 1, 5, and 3 leftovers after that. So again, this is 3 times 2 is 6, that's 11, and 13, 1, 5, and 3, 1. So 3 times 3 is 9, 9 is 1, 5, and 4 leftovers. 3 times 4 is 12, which is 2 5s and 2 1s. And finally, 4 times 4 is 16, which is 3 5s and 1 left over after that. So here is my base 5 times table. Let's just move it down so it's all on one page so we can take a look at it this way. So now I can kind of think about doing my multiplication using the standard multiplication algorithm, 32 times 32 or 32 times 13. So I'll put this 32 and then I'll put 13 and I'll think about just doing the multiplication algorithm. Okay, so 3 times 2, and I'm using now my times table when I do this. 3 times 2 in my times table is 11. So I'm going to put this as a 1 over here in the ones digit, and then I'll carry the 1 up into the next position. Now I'll take 3 times 3 in my times table. 3 times 3 is 14. Add 1 to that, so that's 15, which in base 10 is now 20, and I'll put that over here as my 20. Now I'm going to do the 1 times 2 in my times table. That's going to be 2. And now moving over the 1 times 3, which is just going to be 3. So I'm adding the 201 and the 32 with the implied 0 there. And now I'm going to get 5, 2, 1. Of course, there is no 5, so that's going to become a 1, 0, 2, 1 in the base 5 system. So I hope you were able to kind of follow this, but the key was using the standard multiplication algorithm. But every time I add or multiply, I need to make sure I'm adding and multiplying using the base 5 operations instead of the base 10 operations. Let's go back and check to see that I got it right. 1, 0, 2, 1, base 5. All right, hope you've enjoyed this video. We'll talk to you next time.